Hey there, chemistry students. This is Ms. Ruark. This is Vodcast 2.2. We're going to start looking at how to locate electrons, or how to tell where electrons are located at in the atoms. Okay, so we have a couple different ways we do that. In the last vodcast, you learned about quantum numbers, and in this vodcast, you're going to learn about electron configuration. All right, so in order to do electron configuration, you need to have your periodic table in front of you. And if you look on your notes, you'll see that you have a nice, nifty, handy periodic table here. In your notes, it tells you to label them according to a color and label. You don't have to color, but it says to label them according to the sublevels. So we have 7 main energy levels. We have sublevel for the S is here. Remember, helium should be here in this one, but it's not because it's a noble gas, so it's over here. We have our P sublevel, which would be these nice 6 rows or 6 columns here. Then we have our D sublevel. This is all from your vodcast that you did last night or the night before. And then here are your F sublevels. Okay, so you should have your periodic table nice and organized. All right, one other thing is I told you in the last podcast about quantum theory that when you get to the D's, you're going to subtract 1 from the energy level. N stands for energy level. You learned that in the last podcast. Okay, so you're going to subtract 1 from the energy level. Well, if it's in energy level 1, 2, 3, 4, 5, 6, and 7. All right, so if it's in row 5, it's in energy level 5, but actually it's in energy level 4. So we would start with number 4 here. We would start with number 3, number 5, and number 6. When you get down here to the F's, we subtract 2. Okay, so this would actually be 5, and or not 5, I can't count. This would actually be 4, and this would actually be 5, because the energy levels are overlapping. Okay? They overlap, which means that the 4S is actually a little bit lower in energy than the 3D. Okay? And if you're confused about that, I'll explain it a little bit better in class and show you some examples. Okay, so we use something that's called off-ball diagrams, and an off-ball diagram is something that we use. It's another name for it is an orbital diagram or orbital notation. Okay, what it shows you is it shows the orbitals as boxes or as lines, and it splits it up. It's just a nice visual representation of an electron configuration. Okay, so off-ball is a word that means to build up or to go from the bottom, to fill up, to build up. Okay, off-ball diagram shows electrons. This is wrong. This should be off-ball principle. Sorry. So anyways, the off-ball diagram, an electron configuration, is governed by 3 rules. One of them is the off-ball principle, which is electrons fill the lowest energy levels first. The second rule is Hund's rule, and it says that every suborbital gets 1 electron before they get any pair of electrons. And then the Pauli exclusion principle says electrons in the same suborbital must be of opposite spin. Okay, and we represent the spins of electrons using up arrows and down arrows. Now, you'll notice when I start doing mine that I do a half arrow, and you can choose which one you want as long as you show it. All right, so just to give you an idea, I talked about the orbitals and the shapes of the orbitals in the last vodcast. Well, this is an example of what they look like. The S is a spherical sublevel. It's a spherical orbital. Okay, so it's a spherical. A sphere is a 3-dimensional circle. Okay, the P sublevel here is a parabola, so it's got a bump and it's got a bump. Kind of looks like an 8, right? Well, when you get to the D, they're a mixture of P's and S's put together. Right? And then when you get to the F's, it's a bigger mixture of all of them put together. So here, in your S sublevel, there's only one way you can orient this, and so there's only one orbital or one orientation. Right? In the P sublevel, we can orient this around the X, the Y, and the Z axis, and so there's three orbitals. Right? 1 orbital. Here we have 5 different ways that we can represent it around the X, the Y, and the Z axis, so this has 5 orbitals. And this one has 7 different ways that we can represent it, so there would be 7 orbitals. All right, so, and yeah, I think that was it. Okay, so why is that important? Well, when you do your off-ball diagram, you'll show these orbitals as dashes or as lines or as boxes. Okay, so just to show you, oh, and then one more thing is that each one of these orbitals is filled with 2 electrons. So 2 electrons go into each orbital. So the s orbital can hold a maximum of 2 electrons. So the p orbital, s orbital can hold 2 electrons maximum. The p orbital, or the p sublevel, excuse me, can hold a total of 6 electrons maximum. The d sublevel can hold a total of 10 electrons max, and the f sublevel can hold a total of 14 electrons max. They can always have less, but they can't have more. There's just not enough space. Okay, and each one has opposite spin. Remember, opposite spin. Okay, so here's an example of what an off-ball diagram would look like if it's not filled in. And this just shows how the energy levels are associated with the different sublevels. So the lowest in energy is the 1s, and then as you go up, it increases energy. So the 1s and then the 2s. The 2s is higher in energy, 2p is higher in energy, 3s, and then 3p. And then look here, the next one up is 4s, and then the next one here is 3d. So it's just a little bit higher in energy than the 4s because it slightly overlaps with it. And then you have your 4p and then your 5s, and your 4d, again, is slightly higher in energy than the 5s. And then you keep going, you've got 5p, 6s, and then the next one is 4f. Well, look, that's the 4th energy level, and look how far it's overlapped. It is overlapped so much that it's higher in energy than, of course, the other 4s, but it's higher in energy than the 5s, the 5p, and the 6s. Okay, it's all due to overlapping of those energy levels. Okay, how does this work? Well, let's say that I wanted to have you do the orbital notation for helium. Let's not do helium. Helium would be too easy. Let's do it for boron. Okay, so if I asked you to do the off-ball diagram for boron, you would have to draw it this way, where the energy levels are increasing. If I asked you to do just the orbital notation, you could do it sideways. Okay, either one is fine, really. Alright, so for boron, boron is here, and it's in the 2nd energy level. And if you remember, I said this was the p sublevel. So it's in the 2nd energy level, the p sublevel, and it's the first box into that sublevel. Okay, now, in order to show the orbital notation or the off-ball diagram, you have to start from the beginning, and you have to show that you filled in all these electrons to get there. So boron has a total of 5 electrons. Alright, so we've got to fill in 5 total electrons as we go up. Well, the easiest way to do it is start at the bottom. So we're going to fill in 1 and 2. And then we're going to fill in 3, 4, and 5. And that's it. Alright, 2p, and there's only 1 electron. So it matches with that. Okay, now, I know that you just wrote on this. Hopefully you wrote in pencil. I should have warned you beforehand, but let's try another one. Okay, let's do one that's going to be a little bit more difficult than that. I don't want to be super easy. Okay, so let's look at, let's say we have sulfur. Okay, sulfur is in the 3rd energy level, and it's in the p subblock. So we are going to have to go until we get to here. We're going to put a total of 16 electrons in there. So we're going to fill in 1, 2, 3, 4. Now, each line gets 1, 5, 6, 7. Then we fill in with our second line. Yeah, there we go. So that's 10. Here we have 11, 12. And then when we get to the P, each line gets 1. Right, so that's 12, 13, 14, 15. But we need 1 more, so we go down 16. And now we have our 16 electrons. Okay. Hopefully that makes sense to you. Yay! Alright, let's move on. We'll practice some of this in class. Okay, so long-hand configuration, or long-hand electron configuration. So this just gives us a chance to put it all together. The long-hand configuration, gives the probable location of an address or address of an electron. And now, notice I said probable. It does give a lot of information, and it does use the SPDF notation. So how does this all work? Well, let's look at our periodic table. We just did the electron configuration for boron, and we did it for sulfur, or the orbital notation for boron and for sulfur, right? So let's go ahead and do the electron configuration for those. Remember, these are energy levels 1, 2, 3, 4, 5, 6, 7. Remember, this is the S subblock. This is the D subblock. The P. And these are the F's down here. And don't forget, when you get to D and F, you subtract from the energy level, N minus 1 and N minus 2. Okay, so to get to boron, we need to fill in 5 electrons. And just like we did on our off-ball diagram, we always have to start at the beginning. Now, when we did our off-ball diagram, we started here, and we went to here, and we filled in 1s, and we put 2 electrons there, right? So, oops, I went too quick. Let me show that diagram real quick. We had, for boron, we had 1s, we had 2s, and then in our 2p, we had 1 electron, right? So your electron configuration is going to say 1s, and in the 1s, there's 2 electrons. In the 2s, there's 2 electrons. And in the 2p, hey, guess what? There's 1 electron. And that is your electron configuration. Now, how can you get that just by looking at the periodic table? Well, if we start here, we always start here, and we're going to read it like a paragraph. So we start here, and we say this is the first energy level. It is the S subblock, so 1s, and we fill in 1, 2 electrons. Moving to the next row, this is the second energy level. It is the S subblock, so 2s, and we fill in 1, 2 electrons. So we write that there. And then we keep going. We're in the second energy level still, P subblock, and we fill in 1 electron. Alright, so what I want you to do is I want you to pause it and try sulfur. Okay, so you should get 1s2, 2s2, 2p6, 3s2, 3p4. Alright, and then when you get to class, I'm going to try some of here with the well, here, let's do one real quick. Let's do scandium. Alright, when you do scandium, again, you start at the top, 1s2, 2s2, 2p6, 3s2, 3p6, because we've got to keep going across, okay, 4s2. But remember, when we get here, we subtract 1 from our energy level, so it goes down to 3. It's the D sublevel, and it's the first electron N. Okay, now, here's the easy way to do it. It's called shorthand or noble gas configuration. The noble gas represents a stable or full outer energy level, and they're used to represent all but the valence or the outside electron. Okay, so how do you do this? Let's go back. All right, how do we do this? I need a periodic table, so I'm going to go back to the periodic table. All right, let's say that I want to do scandium. Okay, if I want to do my noble gas configuration for scandium, I find scandium, I go up 1 row and all the way over to the right, and it's argon. Argon is the closest noble gas that would be like scandium. We fill it in brackets. We say that scandium has everything that argon has, and it also has 4s2 and 3d1. And that's your answer for shorthand notation. It's a lot easier, right? Now, here's the big thing. Make sure that you don't give shorthand notation unless I ask for it. If I ask for electron configuration, you have to give me the whole thing, especially if it's down here. Yes, even if it's down there. Okay? All right, so that should be enough to leave you for the day. Here you go.